Welcome to the last lecture in this fluids course. Okay, so you will see that we're going to be doing examples questions today. Okay, so hopefully you all had a chance to look at the questions. These are basically past exam paper questions, okay, so they are exam type questions. Okay, shh. Excuse me. Thank you. Okay, so in the course on Monday, we introduced some key concepts about open channel flow, and we met the concept of open channel flow and flows with a free surface. We met the Froude number for the first time, which is this number that characterizes the flow, whether it's subcritical or supercritical. We also met total and specific energies for open channel flows, and we also, at the end, analyzed the hydraulic jump. And finally, at the end, I left you with one question. It was actually a challenge, okay? So this was a picture of a hydraulic jump in a real structure. And I said, your task, if you choose to accept, is to find a hydraulic jump in your accommodation. And my hint was, look in the kitchen. So what's the answer to this? Well, is it in the washing machine? No, it's not. Is it in the fridge? No, it's not. Okay, where is the hydraulic jump? Yes. It's in your sink. Okay, good. Some people got it. So this is a picture of my sink, okay? And what you can see, here is the water from the tap coming down, and then it strikes the bottom of the sink, and it goes out in the radial direction very, very fast. But that's too fast for friction losses, okay, due to the bottom of the sink. And then you get this hydraulic jump just here, all the way around. Okay, so this is a hydraulic jump. So you have been looking at hydraulic jumps all your life and probably never realized it. Okay, so that's where the hydraulic jump is in your accommodation. Okay, so the objectives of today's lecture are to go through two questions, and they've got two different themes. The first one is using conservation of mass in the Bernoulli equation with a discharge coefficient. And the second one is using conservation of momentum and working out a drag coefficient. Okay, so these are two different parts of the course, and we're sort of bringing it together in an exam question. But before we do that, I want to give you some advice on doing well in exams. So in January, you've got your first set of university exams coming, and you've never sat exams in a university setting. So I wanted to give you some points from my experience, both of having been a student, sat where you are, and then also having been an academic and teaching and marking and all of these sort of things. So this is my sort of top advice for doing well in exams. So first of all, you've got a break coming up over the festive period. This is where you should take the time and the space to consolidate what we've covered, not just in the fluids course, but in all your other courses. At university, we move at pace through the material. The lectures are the starting point for your learning. The responsibility is on you to go away after the lecture and really try to understand and learn the material. But often, we're going at quite a pace, so you don't have the time to really understand it all. So make sure you spend time after you've had a rest during the break to really understand the material. So that doesn't mean memorizing it. It means understanding it, understanding the concepts. How did you get from here to here in the theory or the application? Then there is no substitute, once you've understood it, to attempting as many worked examples as you can to increase your experience in answering questions. The best source of questions are the Schaum outline books, not just for fluids, but for all different topics and maths and materials and all that sort of thing. Each book has got thousands of questions in, worked examples with solutions. On the Blackboard page for fluids, you'll see there is a link to the Schaum book for this course, but you should use that just as a starting point. Thirdly, I strongly advise, just as you probably did when you were in high school, to do a past exam paper under exam conditions. So if it's a 2-hour paper, sit the paper on your own, in quiet, for 2 hours, trying to do the answers. And then when the 2 hours is up and you've gone through the process of doing that exam, then you look at the work solution. So really push yourself and test yourself. This is how to prepare yourself for the real exam. It also gets you used to using your time, which I'll come to in a second. And fourthly, doing well in exams, you can be really good at points 1 to 3 there of understanding material and answering it and practicing past papers. But if you get your strategy wrong in the exam, you're going to do terribly. Okay? You won't do as well as you could do. You won't get as many marks. So what's my strategy for doing well in the exam, during the actual exam? The first thing is, at the beginning, give yourself 5 to 10 minutes just to read all of the questions. Identify how many marks there are for each question. Some exam papers have got a section A and a section B, and the questions in section A have a different number of marks to the questions in section B. So make sure you understand the structure of the paper. Make sure you identify the questions that you think you can do and the questions that you think you cannot. Then you need to give yourself 5 to 10 minutes at the end to tidy up your exam script, to make sure everything is readable and clear. It's very frustrating for us when we can see someone who's kind of understood what they're doing in the exam, but we can't read it because the writing is terrible, or we just cannot find the answer because it's so messy. We can't give you the marks if we can't see the answers. So give yourself time at the end to tidy everything up. That 5 minutes tidying everything up could get you an extra 20 marks because suddenly everything is readable and findable. It sounds obvious, it sounds basic, but the number of times we mark exam scripts where that's not been done, it's very, very clear. But the person who's disadvantaged is you. Okay? So, you've got 5 minutes at the beginning you've got to give to read all the questions, 5 to 10 minutes, 5 to 10 minutes at the end to tidy everything up. So from the time remaining, now you can work out how much time you should spend on each question. So if, for example, you have 4 questions to answer in a 2-hour exam, 2 hours is 120 minutes. You've got 10 minutes at the beginning, 10 minutes at the end, so that's 20 minutes allocated for reading and tidying up. That leaves 100 minutes for 4 questions. That's 25 minutes per question. Okay? That's easy structuring of your time. But here's where a lot of students go wrong. Once you have used the time that you have allocated for a question, move on to the next one. You might think, oh, I'm nearly finished. I can get all the marks in that question. I can get the last 5 to 10 marks, whatever, just another 10 minutes. No. Move on to the next question, because you've already given yourself 5 to 10 minutes at the end to go back and finish off those questions that you couldn't finish. So this is the strategy of how to do well in an exam. Because on the day, you don't know how you're going to feel. You might be very stressed. You might have not slept very well the night before. So this is a strategy to make sure that you always get the best out of yourselves, no matter how you're feeling. Okay? So I really wanted to share that with you so that you guys can do as well as you can in the exams and do yourselves justice. Right, so let's move on to the questions. Notice with this question, there is no image, there is no figure, so you've really got to read the question carefully. A cylindrical tank of base diameter 0.5 meters is used to store water. A rupture at the base of the tank allows water to escape through an aperture of area 8 centimeters squared. A discharge coefficient of 0.6 can be assumed for this orifice. If the depth of water in the tank is initially 0.8 meters, how long does it take to empty the tank? Okay, so it sounds a relatively simple question. The question doesn't tell you how to answer it. So you've got to start thinking now, okay, do I use momentum? Do I use conservation of mass? Do I use energy? Or do I use Bernoulli? What do I use? The way I approach questions is that I write down what I know, okay, and I try to understand the question and communicate that. So, as I say here, the question contains no diagram. So the first thing is to draw a diagram to check the understanding. If you draw a diagram in the exam, you're likely to get marks because it's showing that you're understanding the question. You're understanding maybe the physical processes involved. You're communicating your understanding to the examiner. So draw a diagram, because not only will it help you, it will help us to give you marks. So here, this is the diagram. So we've got a cylindrical tank, okay? We've given it a depth of water h. Here's the surface area here, AS. Here is the rupture, basically, the orifice at the bottom. And we know that's got a diameter because we're told that. And it's going to have a velocity and a flow rate out. And we're being asked to find the time taken to empty that tank. So we know we've got to think of time. Okay, we have to think of time. We want to find the time for the depth and the velocity to go to 0. So what's the volume of the tank at any particular time? Well, it's going to be the depth of water times the area. That's the volume. So the question really is how does that change with time? Then how do we use that change in time to work out the time to empty the tank? So let's set up our problem. This is now we've drawn the diagram, we can begin to think, this is a conservation of mass problem rather than the conservation of momentum. We're not really needing to work out any forces here. We're needing to work out what the mass is and the mass flow rate is. So that begins to lead us automatically then to how we solve the question. So we're told that the diameter of the tank is 0.5 meters, and we know that the area of the tank is just pi d squared upon 4. So, okay, we know what the area of the tank is. That's a known quantity. There's no inflow into the tank. We're not told anything about any inflow. So we can say, well, the inflow rate, Q in, must be equal to 0. And then we're only interested then in the outflow rate. So to find the outflow rate, we know from the topics we've done in this course that we can apply the Bernoulli equation to find the idealized outflow rate, but this is modified by a discharge coefficient. So we were told in the question that there's a discharge coefficient. Yes?
I know how to do the question. I think I got the question wrong, but I think I'd like to provide my own idea on how I did it.
Okay.
I used V is equal to 0. I used V actual.
I'm sorry, I'm going to interrupt you. I'm going to leave that until the end. Okay, I'll look at your solution individually at the end, but right now I'm just going to go through this solution for all the audience, okay? I'm very happy to look at people's solutions at the end, but right now I'm just going to work through the Wirt example, okay? So here we have the outflow, and we know we can apply Bernoulli to find the idealized outflow rate. And it's modified by a discharge coefficient. So our actual outflow rate is equal to our ideal flow rate times the discharge coefficient. So this is what we covered 1 week ago when we looked at departures from ideal flow. We're still not worrying about the forces. We just want to deal with the conservation of mass principle first of all. So let's set up the conservation of mass for this problem. Now, the principle of the conservation of mass states very clearly that the rate of increase of mass inside our control volume must equal to the net rate of flow of mass into the control volume, okay? So we're looking at the rate of increase of mass and the net rate of flow of mass into the control volume. So this is a statement of the conservation of mass. So when we express that mathematically, well, the mass at any point in time inside the tank is equal to the density times the volume, so A times AS times H. But the rate of change of that mass is going to be the derivative with respect to time. So this is the rate of increase with time. Now, the net rate of flow of mass into the control volume, that's going to be the flow rate in minus the flow rate out. Or I should say the mass flow rate in minus the mass flow rate out. So it's rho Q in minus rho Q out. The densities cancel. They're constant. They're not changing with time, so that's nice and easy. And we're left with this equation. And here we've just gone and substituted in what we know from Bernoulli. If the question is simple like this, in the exam, yes, you can just write that and say, I know from Bernoulli that the outflow rate is going to be equal to the square root of 2gh times the discharge coefficient. Okay, so what you can see now is that we've got an equation in terms of h. Okay, this is the height. And we want to know when that height h goes to 0, because that's the volume in the tank. So if I just do a little bit of algebraic manipulation of the equation, I've basically got a differential equation here in terms of h and in terms of time, and I just have to solve my differential equation. So what I'm going to do here is I'm going to rearrange this equation so that I've got all the terms with h on the left-hand side and all the terms with time on the right-hand side. All the other terms in the equations are just coefficients or properties of the geometry, so area, things like this. Okay, so I'm going to rearrange everything on the left-hand side to have h and everything on the right-hand side to have time. So this is what I've done. So here's time on the right-hand side, so here's dt. And then here on the left-hand side is everything to do with h. This is dh over h to the power half. And then this are just coefficients. At this point, I'm just going to evaluate this little coefficient on the left-hand side. So here I'm inserting all my values. So I've got my area, I've got my discharge coefficient, I've got my other area, and I've got my square root of 2 times g. This leaves me with a nice equation of minus 92.33, that's that coefficient, times h to the minus a half, dh is equal to dt. Now, this is an equation that's clearly telling me to integrate. So I integrate my equation. So I integrate my water depth from its initial value to its final value. The final value must be 0 because we're wanting to empty the tank. And for the time, well, at initial time, time is equal to 0, and then we're wanting to know the total time to empty the tank. So all I have to do now is integrate that equation, and I find capital T, which is the time to empty the tank. So here I have integrated it, so this integrated with respect to time just gives me t, and so between 0 and t, this gives me capital T. And then here I have integrated h to the minus power half with respect to h, and I evaluate that between h0 and 0, and this gives me my final time of 165 seconds. So when you first read the question, you don't know how to answer it. It doesn't tell you how to answer it. But we work through it. We identified the unknowns, and we identified the knowns, the known quantities that we're given in the question. And drawing a diagram is super important for your understanding. So that's a real key point. Okay, so this is question 1. Okay. All right, so question 2 is a bit more involved. So a two-dimensional beam of height 100 millimeters spans a square air conditioning duct of height h, which is equal to 400 millimeters. The approach flow is uniform, and it has a velocity UA is equal to 0.6 meters per second, whilst the downstream velocity profile is two-dimensional, is given by this equation that's misplaced just here, okay? So this is the downstream flow profile, velocity profile, and this is the upstream one, because this approach flow is uniform, 0.6 meters per second. He says, assume the pressure is uniform over the height of the duct at both the upstream and the downstream sections. So that's quite important for the momentum analysis. So it says, assume the pressure is constant. Neglecting drag on the walls of the duct, find this value UB, which is here in the velocity profile. Find the difference in the pressures between the upstream and the downstream sections, assuming that Bernoulli's equation holds outside the wake region. Basically, where friction effects are not important, you can apply Bernoulli. Find the force on the beam, and then define an appropriate drag coefficient for the beam and calculate the value. So quite a lot, but the question is taking you through the steps. Okay? It doesn't say, find the drag coefficient. Okay? The question says, find the velocity, find the pressure difference with these assumptions, find the force on the beam, then find the drag coefficient. So this is very typical of an exam question. Okay? So it gives you information, it has a diagram to explain some of it where it's complicated, and then it gives you the different parts which take you through the solution. So let's get cracking. First of all, we have to find this quantity UB, which is here. Before I do that, I just want you to notice that this velocity profile is given in two sections. So if y is less than h upon 2, then you have this reduced velocity profile because you have a wake, which you now understand, okay, for flow past objects. But when y is greater than h upon 2, it's just equal to a uniform value, so UB. So I just want you to understand that equation and how it relates to what you can see in the velocity profile here. Okay, so let's find that value UB. So W is going to be the width, this duct or this tunnel, okay, and we're going to set it equal to h because we're told it's a square duct. So the first thing we do is draw a control volume, in this case, around the area that we're interested in. So the area that we're interested in goes from point A here, at the arrival of the uniform inlet flow, to point B here, where we have this wake region. So this is our control volume, and we're going to do all of our analysis in that control volume area. We're going to go through the same sort of steps as we did for the previous one. First of all, we're going to consider conservation of mass. But then, because it asks us to find force, we're also going to consider conservation of momentum. So conservation of mass is a steady flow problem. So the mass flow in must equal the mass flow out. There's no change with time like in question 1. So A dot must be equal to MB dot. So the mass flow in must equal the mass flow out. At A, the flow is uniform. So we can write down, literally, the mass flow rate at A. So this is equal to the density times velocity times the area. So there's my mass flow rate at point A. At point B, it's a bit more complicated because we've got this varying velocity profile. So I'm going to use the same technique that I've been using all the way through the lectures, and I'm going to consider initially a tiny element of that exit. So a tiny elemental area, delta A. So I've zoomed into this point here, and I'm going to find out what happens in a tiny element first, and then sum up all the contributions for all the tiny elements over the exit. So in a tiny element dA, that's an area of dA, we have a flow velocity, u. Because this is at a distance y from the bottom wall, the velocity here is u at position y. The height of that element is delta y. So the area of my element is delta A, which is equal to W, the width of the channel times the height, so W times delta Y. So now we can consider the mass flow rate just through that little element. Well, the mass flow rate is delta m dot, which is equal to rho times the velocity times the area, exactly as we did here, rho times the velocity times the area. So now we're doing it just for the little element. So this becomes rho times u times w times delta y. That means that the total mass flow rate across the height of the duct is equal to the sum of all of the mass flow rates through all the little elemental areas. So we sum up all the delta m dots across the height of the channel, which means we're summing this expression over y. Okay, so you could put a little y at the bottom here of this summation. We haven't yet got to the point where we can integrate this. Yes, a question here. W is the width. In which width here, W? Okay. So as before, in order to work out this summation, we make that, oops, I don't know why sometimes my mouse does that. We make that elemental area get smaller and smaller and smaller. Okay, so delta y gets smaller and smaller and smaller, so it tends to 0. And as it tends to 0, we know from our calculus that the limit, as delta y tends to 0, gives us an integral. Now we can evaluate that integral because we know what the velocity profile is. We're given that velocity profile. So our mass flow rate is given by that integral, but we have different expressions or different values for that velocity profile over the height of the channel. So from here to halfway up the channel, velocity profile is given by this cos expression, but above there it's given by a constant value. So we're going to take this integral and we're going to split it up from 0 to h upon 2 and then from h upon 2 to h. So this is what we do. So here is our integral. Here is our mass flow rate at B, integrated in a general form from y is equal to 0 to y is equal to h. And we then integrate from 0 to h upon 2 for the cos function part, and then from h upon 2 to h for the constant part. So this is an integral that you should, that sort of integral that you should have seen hundreds of times, and you should be able to do almost in your sleep with your eyes shut, okay? So we integrate each integral on its own. So when we integrate this one, we've got a 3 upon 4 minus 1 upon 4 cos 2 pi y upon h. So 3 upon 4 integrated with respect to y gives us 3 upon 4y. The cos term gives us a sine when it's integrated, and that's evaluated between 0 and h upon 2 for y. The same here, okay? So rho, w, u, b, these are all constants, so they do not get integrated with respect to y, so you just got y evaluated between h upon 2 and h. So when we plug in all of our values, we find, okay, there is my mass flow rate at B. So rho times w times ub times 7 h upon 8. So this is just evaluating the integral. Okay. Remember, the mass flow rate at A must equal the mass flow rate at B, so ma dot is equal to mb dot. This means we can now equate our two expressions, and we can see immediately we then get the value for ub. So ub is therefore 0.6857 meters per second. So this is how we've done it. So this is really just using conservation of mass to find ub. So that's part A of the question. The next part of the question said, okay, find the difference in pressures between the upstream and downstream sections, assuming that Bernoulli's equation holds outside the wake region. The question also said that the pressures across the duct at A and the pressure across the duct at B are constant. Okay, so they're not varying with the distance y. They're constant across these sections. So outside of the wake region, there is our Bernoulli equation. So PA plus a half rho UA squared is equal to PB plus a half rho UB squared. So a nice application of Bernoulli. We want the difference in the pressures between the upstream and the downstream. So upstream is pressure PA, downstream is pressure PB. So the difference is PA minus PB. So PA minus PB is equal to a half rho UB squared minus UA squared. We substitute in our values. We know this already. We know UA, and this is UB. We just calculated. And there is our pressure drop. Okay, so the pressure is dropping from point A to point B. So that's part B done. So part B was actually quite easy. You just had to note the value of UB from part A. Okay, now let's get on to the real meat of the question, the real, perhaps the most challenging part of the question, which is part C. This is where we are being asked to find the force on the beam. So this is bringing together a lot of what we've done in the course all together in one part of the question. So we use a control volume as we did before, and we're going to apply the steady flow momentum principle. Okay, so the force on the fluid inside the control volume is equal to the net rate of flow of momentum out of a control volume. This is a consequence of Newton's second law. Okay? This is how we apply it to fluids with a control volume approach. So the force on the fluid inside the control volume must equal to the net rate of flow of momentum out of the control volume. So the net rate of flow of momentum out of the control volume is equal to the momentum flux out minus the momentum flux in. We then just need to work out what our momentum fluxes are. So let's draw the free body diagram. So this is where you're communicating to whoever is reading your solution how you understand the question. So here is my control volume that I had earlier, and here is the beam in the middle of it. So what are the forces on the fluid? We have a pressure force. We have a force due to pressure A at the left-hand inlet. We have a force due to the pressure B at the downstream, but we also have a force on the fluid from the beam. So that's the key point here. So here we've got a force acting on the fluid from the beam. So that's the key point. So we can now write our equation for this momentum principle. So the force on the fluid in the control volume is equal to PA minus PP times the area, which is W times H, minus this force from the beam on the fluid. So the force on the beam is going to be opposite. Okay, so this is why I put this here. So the force on the beam is opposite. F here is the force acting on the fluid from the beam. So later we have to reverse that. We have to remember to reverse it. Okay? So those are our forces. Now we just have to work out the momentum fluxes, and then we've done the question. So let's compute the momentum flux in. That's the easy one because we've got uniform flow at the inlet. Well, your momentum flux is basically mass times velocity, okay? But it's a flux, so we have the mass rate, mass flow rate, so ma dot times ua. Well, we know those quantities, so that's rho times ua times aa times ua. But what about the momentum flux out? We're going to do the same process that we did for the mass flow rate, because we've got this complicated velocity profile. So what is the momentum flux across that section? So just as before, we're going to consider a small element, delta A, and we're going to consider what the momentum flux is through that small area. Well, my momentum flux out is therefore equal to my mass flow rate, so delta m dot out. We actually know this because we worked it out in part A of the question, times the velocity at that point. So here's my velocity out again. Okay, so here is my momentum flux out through a small elemental area, delta A. So this gives me rho times u times delta A times u. So over the whole section, over that whole area, the total momentum flux is going to be the sum of all the contributions to the momentum flux out for all the little delta A's across the width of the channel. So this is the sum of all the momentum fluxes out. Well, here's my expression for momentum flux, so rho w times u squared dy. And we sum from y is equal to 0 to y is equal to h. What happens to the summation as my height, delta y, goes to 0? Yes?
I'm reading ahead of the question, and I found that we're supposed to turn the summation into an integral.
Exactly.
We have a far simpler idea. We can take the mass flow rate value from earlier and multiply u. Multiply uy with that, or that's not how it works.
No, you can't, because it's varying. That's the difficult part of the question. So it's a good point. You can't just take your answer from part A and multiply it by your total velocity across B. You have to do it this way. That's a good point. So our summation as delta y goes smaller and smaller and smaller becomes an integral. Okay, so our summation becomes an integral, and so our momentum flux out is now just our integral of rho w u squared with respect to y across the width of the channel. Or height, sorry, not width. So let's evaluate the integral. This is just maths, okay? So we have to split up our integral into two parts, from 0 to h upon 2 for the first part, which is clearly varying. And then we have to do the final part where the velocity is uniform. So here is our integral from y is equal to 0 to y is equal to h upon 2. And now note we've got u squared. So this is ub squared into all of this lot squared. And then this is our expression from h upon 2 to h. So as long as you are careful with your algebra, this part of the question is just routine. So first of all, the way I solve this is I multiply out my square bracket term here. So I end up with all of this. I've got a cos term and I've got a cos squared term. And at this point, when you're integrating a cos squared term, you remember that you have this identity, this trigonometric identity, and we're going to use that in our integral. So we substitute that term into our integral. So all I've done is I've substituted cos squared into here to get this term here. And now I have an equation that I can integrate, and I have integrated it, sorry, and it's given me these terms which I evaluate between 0 and h upon 2 and h upon 2 to h. So it's a little bit laborious, but this is just maths at this point. So if we complete the integral, we end up with our momentum flux being actually a very simple expression. So rho w b squared h times 51 over 64. So this is just the result of our momentum flux out. This now allows us to compute our force, okay? So this was our momentum equation we had earlier. So PA minus PB times the area minus the force F must be equal to the net rate of momentum flux out of our control volume. So we put in all of the values that we've got. So here's our momentum fluxes going into our equation. We rearrange for F because that's what we're after. So F is equal to all of this expression. I've just rearranged this equation. I have my equation here, so this is, if I just go back, this is the same equation as at the bottom. I've just rearranged it. So there is my expression for F, the force F, and I put in my values, this rather small value for F, so 7 times 10 to the minus 3. So this is the force on the fluid. Okay, so this is the force in the negative x direction. So the force on the beam is equal and opposite. Okay, so you would be minusing that. And that's the final answer of the part C of the question. So we found the answer. But as soon as something says find the force, or find the drag coefficient, which is really a force over a certain quantity, it's asking you to use conservation of momentum. So that momentum principle. So finally, the drag coefficient, which we met last week, the force on the beam over a half rho u squared times the area. In this case, the area is this height of the beam, 100 millimeters times the width of the channel. We put in all our values, and there is our drag coefficient. So part D of the question is one line. Okay, it's very, very quick, but working out the force is quite involved. Yes?
Why do we use rho as 1.2? I wasn't given in the question.
It says it's a air, I think. It's 1.18, strictly speaking. You could have used 1.18 or 1.2. If you say, okay, I'm told in the question the gas is air, I'm therefore taking this value, it's okay. Okay, so it's a good point. If you're given a question where you're told the gas is air or something like this, and you have a data book, but you're not given explicitly the value for the density, you have to state which value you're using. And therefore, in this case, we're using 1.2. Yes?
Is there any way that someone can help me feel less terrified about this? And does it get any harder?
How to feel less terrified? Well, that's a personal question.
But I want to ask, does it get any harder with this?
My advice is understand what's going on. If you understand what's going on, you can work your way through it. And that's why I say practice questions. That's why I say go to Schaum book and practice questions.
So reasoning over questions is a good way of getting understanding.
Yeah. So answering questions is a good way of forcing you to understand. I think there are probably worse things in life than a question on a fluids exam paper. That's my personal opinion on it. Okay, so in this lecture, we've covered some key concepts. One is exam strategy, and one is working through 2 worked examples. This is the last lecture in the series, so before I get onto my last slide, on Monday, the plan, okay, is to use the lecture slot with me and a couple of the graduate teaching assistants to go to the lecture room on Monday and be there to answer your questions, okay? However, as many of you will be aware, last night the government said the advice is that we should be working from home from Monday onwards. I haven't read my email yet this morning, so I don't know if the university is going to tell us to work from home on Monday, okay? If we're not working from home on Monday, we will be in the lecture theatre on Monday at 10 o'clock, and you can come and ask us questions and try to clear up any problems that you've got. So that's on Monday, but the last thing, now hopefully this works. So this is a bit of fluid mechanics that was produced by NASA. where they use their satellites to look at the movement of currents in the ocean over many months. And so here you can start to see some of the many parts of fluid mechanics that you've been studying this semester. With everything from friction to viscosity, it's all here. And this is one of my favorite sort of visualizations of fluid mechanics. So the last thing I want to say is that last year we were all teaching online, and it was very challenging for all of us. And I have thoroughly enjoyed teaching face-to-face this semester. And I've thoroughly enjoyed interacting with you all and having an awful lot of fun with fluids, okay? So thank you very much. And I hope you all do really well in the exam, okay? So hopefully we see you on Monday, but we'd never know.